Okay, moving on to the second chapter, we start with these definitions of orderings on sets. We call an ordering a partial order if it is anti-reflexive, that is to say, for any element of the set that we may be defining an order on, that it is never less than itself. That's anti-reflexivity. Transitivity is that if P less than Q less than R, then P less than R. These are two pretty primitive things that we want from a strict less than sort of symbol. Now, one thing that obeys these kinds of rules is, for instance, the strict subset ordering on sets. This is a partial order, and of course nothing is a strict subset of itself, and this is a transitive ordering. So that is an example of a partial ordering. Now, in economics, or maybe game theory, or wherever you might encounter this, there is the preference ordering or utility ordering or something like that, where possibly some two things that you might have a preference for are not comparable, right? You don't necessarily prefer one to the other, nor are they equal. So in preference theory, I think it's called, we sometimes define this preference ordering, which does have to satisfy anti-reflexivity, that you never prefer a thing to itself, and it is transitive for obvious reasons, I think. So these are just some examples of partial ordering, but what a partial ordering is, so to speak, lacking is commensurability, or at least that's the word that comes to my mind when I think of this property, that, for any two things, either one is less than the other, or they're equal, or the other is less than the one. So that just means that any two things can be compared according to this ordering relation. And so these two are examples where you cannot necessarily use the ordering to compare any two arbitrary things. The only example that comes immediately to my mind is the less than ordering on numbers. Now that I think about it, I guess actually the property of there being an injection from one set into another, or even an isomorphism from one, say, group into another group, is a linear, or I guess that's an example of a partial ordering. So in any case, but the examples that I have written here are certainly examples of each of these concepts. So next in the text, the author gives all these definitions for commonly understood words like greatest, upper bound, so on, so I don't feel the need necessarily to talk too much about them. They go very straightforwardly. Next we have this definition of order-preserving functions and then linear ordering functions. All right, so suppose that we have a partial order on P and Q, and it has the property that whenever x is less than y, then applying the function to each preserves this order. Of course, that means that the function is order-preserving. If it were in fact a linear ordering, we would call the function an increasing function for somewhat obvious reasons, but I find it, possibly worthwhile. I mean, maybe this is too much of an obvious point, but this is in fact why, say, we can add something to both sides of an inequation, but if we multiply by a negative number, well, we are in a sense applying the function f of x equals negative x, which is not, in the intuitive sense or in the calculus sense or whatever, an increasing function. That's a decreasing function, and therefore we have to reverse the inequality, and likewise for applying the reciprocal function. So I think that's kind of worth thinking about, that this definition of a linear ordering being increasing is defined in terms of preserving the less than relation is kind of relevant to this fact that we all memorize blindly in high school, so that's kind of neat. An example of an order-preserving function would be one from sets to the natural number, arbitrary set x to the natural number, x ordered by the subset relation. I suppose I should specify that, in fact. And the natural number is ordered by the less than relation, and we map according to the cardinality. I'm kind of using a word that comes up in a future chapter, but we all pretty much know what a cardinality is, at least for the most part. So using this mapping a set to its cardinality is, in fact, an order-preserving function. If you have a superset, then a strict superset, then the size of that should be larger. Ooh, I am totally wrong about this, but it's instructive to think about why. I guess I'll leave that as an exercise and end the video.